So good morning. So what we are going to see the Fabino. So today's topic is about the robot motion planning. So in the motion planning, அப்படிங்கிற term வந்து will be used in the robotics for the process of breaking down desired movement tasks, okay, into discrete motions. So which satisfy uh, movement constraints and possibly optimize some aspect of this movement. Okay, so we'll have a motion planning. So motion planning அப்படிங்கிறது பார்த்தோம் அப்படின்னா which is a term which is used in a robotics for the process of breaking down a desired movement tasks into discrete motions that satisfy movement constraints and possibly optimize some aspect of the movement. Okay, how will be having offer? So what is the difference between the motion planning and the path planning? So path planning அப்படிங்கிறது பார்த்தோம் அப்படின்னா so actually it is the process usually we use to construct a path from a starting point to an end point. Okay, so which given a full, partial or dynamic map. Whereas in case of a motion planning வந்து பார்த்தோம் அப்படின்னா it is the process by which we can define the set of actions which need to execute to follow the path that we had planned. Okay, so இதுதான் வந்து path planning and motion planning the difference. Okay, so when you are defining a path planning அது வந்து பார்த்தோம் அப்படின்னா geometric path இருக்கும், we'll have some issues that is by means of an obstacle avoidance and shortest path இருக்கும். Whereas the case of a trajectory planning வந்து பார்த்தோம் அப்படின்னா we'll have a interpolate or approximate the desired path by a class of polynomial functions இருக்கும். We'll generate a sequence of time-based control set points இருக்கும் for the control of manipulator from the initial configuration towards destinations வரைக்கும் இருக்கும். சரியா? Uh, this is the way we'll have of one robot motion planning. So இப்போ navigation and path planning பார்த்தோம் அப்படின்னா ஸோ global navigations வந்து completely known environmentல இருக்கும், local navigations வந்து with the unknown and partially known environmentல இருக்கும். ஸோ இந்த path planning algorithm வந்து பார்த்தோம் அப்படின்னா for a known environment வந்து is based on classical approaches இருக்கும். ஸோ யூஸ்வலாக என்ன பண்ணுவோம் அப்படின்னா we have to define the task. ஸோ அந்த டாஸ்க்லேருந்து we have to go for the task plan. ஸோ task planலேருந்து we'll be coming for an action plan. ஸோ action planலேருந்து we'll have a path plan. ஸோ path planலேருந்து we'll have a trajectory plan. And finally we'll have a controller. So controller followed by robot and we'll have a sensors. Okay. So sensors will be given to the controllers over on it. Okay. So next time வந்து பார்த்தோம் அப்படின்னா so definition. So we have to define configurations. So this is to be specifications of all the variables that define the system completely. So we have to example go for a configurations of a role. So configuration space on the பார்த்தோம் we'll have a C space. So set of all configurations இருக்கும். Similarly, we'll have a free configurations இருக்கும். That is a configuration that does not collide with the obstacles. Okay. So free spaceல பார்த்தோம் அப்படின்னா set of all free configurations இருக்கும். So it is a subset of C. So when you are going for a path versus trajectory, so path அப்படிங்கிறது பார்த்தோம் அப்படின்னா a sequence of robot configuration in a particular order without regard to the timing of this configurations. This trajectory எடுத்தோம் அப்படின்னா it concerned about when each part of the path must be attained to the specifying the time. So we have to define the path planning for problem definition. So that is we have to compute a collision-free path for a rigid moving object among static obstacles. So input என்னென்ன தேவையா இருக்கும்? We'll be requiring the geometry. How does the robot move? What about the kinematics? And what are all the initial and goal robot configurations? Similarly, output வந்து பார்த்தோம் அப்படின்னா we'll have a continuous sequence of collision-free robot configurations by connecting the initial and goal configurations we'll have over there. So trajectory planning பார்த்தோம் அப்படின்னா there is a while you're defining the problem, we'll have a turn-specified Cartesian space trajectory into an appropriate point positions. So input வந்து we'll have a Cartesian space path and we'll be having the path constraints including velocity and acceleration limits. Output பார்த்தோம் அப்படின்னா a series of joint position or velocity reference values வந்து will be sent to the controller. So this is the block which shows that we have to define the path specifications and we have to define the path constraints for the continuity and smoothness. So we'll have a trajectory planner. With that, we'll be having of a joint space and Cartesian space. So joint space notations will have a Q, Q dot, and Q double dot. So sequence of control set of points will be along the desired trajectory. Whereas in the case of a Cartesian space, we'll have a P, V, and A of T. So joint space versus task space. So joint space பார்த்தோம் அப்படின்னா that is the descriptions of the motions வந்து to be made by the robot by its joint values. Whereas the case of a task space பார்த்தோம்னா the motion between the 2 points is known at all times and it's controllable. Whereas motion between the 2 points in joint space வந்து is not predicted over on it. So it is usually to visualize the trajectory, but it is difficult to ensure singular approaches. So task-based planning sequential motions of a robot to follow a straight line, Cartesian space trajectory under the trajectory specified in Cartesian coordinates which force the robot to run it itself. That is, the trajectory may require sudden change in the joint angles. So path is not in the workspace. We'll have a start and goal in different solutions and branches. So we have to flip between the configurations. Whereas in case of a trajectory planning, we'll have two different types of motions, path to point motion, and we'll have a continuous path motion. Point to point motions பார்த்தோம் அப்படின்னா we'll have a teach initial and final points. So intermediate path is not a critical one and it is computed by the controller. Applications வந்து பார்த்தோம்னா we'll have a moving of parts, spot welding, automated loading and unloading of machines, pick and place motion. Continuous path motions வந்து பார்த்தோம் அப்படின்னா used when there is a need to follow a complex path through 3D space, possibly at high speeds. So points generally turned by manually through which high speed automatic sampling over. So point to point motion. So simple point to point smooth trajectory with a few constraints on the lift off and set down positions. So we'll have a 3 days a manipulator which can move from point to point. We'll have a sleeve motion, we have a joint interpolated motion, we'll have a straight line motion. So sleeve motion part all joints move to the required knee position as quickly as possible. All axes begin motion at the same time but arrive at the destination at different times. So this generally results in joint gear and unpredictable arm motions, whereas in the case of joint interpolated motions, it requires the controller to calculate which joint will take the longest to arrive at the destination and slow other joints down accordingly. A separate velocity will be calculated for each axis and will have a manipulate motions is generally smooth and the wear will be reduced over time. Whereas the case of a straight line motion is a particular case of continuous path motions. So point to point motions joint based trajectory will be using over on it. அதே மாதிரி lift off and set down points will be provided for satisfying acceleration constraints. The cubic polynomial trajectories we'll have a single joint degree of freedom. So theta of naught and theta of f so both will be depending with on each other over on it. Okay. So similarly, we'll have a fourth constraints இருக்கும். அப்போ cubic polynomial எடுத்தோம் அப்படின்னா a0 plus a1t plus a2t square plus a3 t cube இருக்கும். So cubic polynomial trajectory எடுக்கும்போது we have to go for the boundary conditions that is position at t is equal to 0, position at t is equal to final. Similarly, velocity at t is equal to 0, velocity at t is equal to final. அப்போ cubic polynomial எடுக்கும்போது when you are differentiating the expression, we can able to get the value of an a1 plus 2a2t plus 3a3 t square. So when we are clicking all these things, so we'll be solving the value of a3 and a2. We'll get the expression 3 by 3f squared of theta minus theta and minus 2 of 3 by f theta. So thus we can able to find the value of an a2 and a3. So we have to find out the two conditions with the value of an initial and final velocity to be 0 and the value of acceleration. So final expression what we are getting over the value of a0 is equal to theta of naught and this a1 is equal to 0. So only the value of a2 is equal to 3 by 3 x squared of theta minus theta naught and a3 is equal to 2 by 3 x squared of theta minus theta naught. So acceleration பார்த்தோம் அப்படின்னா that is we have to do the 2 times multiplication of this value. So we can able to get the value of theta naught. So theta and this over. And next time we'll be going for an quintic polynomial trajectory. So in the case of an quintic polynomial trajectory, so we'll have a cubic which allows us to define the position and the velocity. Okay, so at each location in that trajectory. So when we are saying about an acceleration about the quintic polynomial, so accelerations will be the discontinuous wave. So if you want to specify the acceleration we have to go for an 5-order polynomial. So for what we have seen about an cubic polynomial. So in order for the quintic polynomial, we have to consider 5-order polynomial by considering the initial and final positions and velocity and the acceleration or to be the boundary conditions for solving our coefficient. Okay. So let me consider the 5-order polynomial. We have written with respect to the matrix over on it. Okay. So that we can able to solve the values and we have to find out the inverse for each joint so that we can able to find out the solutions for that. So what are all the boundary conditions we'll be requiring? We'll be having of an initial position, initial velocity, initial acceleration. Similarly, we'll have a lift off position and what about the continuity in its position, velocity and acceleration. So either T1 and T2 ரெண்டுக்குமே வரும். So lift off வரும்போது we'll have a set down position. Similarly, initial consider பண்ண மாதிரி we'll be requiring about an final position, final velocity and final acceleration. Okay. So இப்போ known parameters அப்படின்னு எடுத்து பார்த்துக்கிட்டோம் அப்படின்னா initial and final values தெரியும், intermediate values தெரியும். ஓகேவா? ஸோ இதுல எல்லாமே what we know it of அப்படின்னு பார்த்தீங்கன்னா we know about an position, velocity and acceleration. So position given இருக்கும், usually velocity and acceleration will be 0. So கொஷின்ஸ் கொடுத்துருப்பாங்க. வெலாசிட்டிஸ் அப்படிங்கிறது பார்த்தோம் அப்படின்னா, ஸோ வி ஹாவ் டு கண்டினியூஸ் வித் த ப்ரீவியஸ் ட்ரெஜெக்டரி ஸ்டேட்மெண்ட். ஸோ அப்போ சொல்யூஷன் எடுத்தோம் அப்படின்னா, ஃபார் எக்ஸாம்பிள் இப்போ nth ஆர்டர் பாலினாமியல் எடுத்தோம்னு வச்சுக்கோங்களேன், இட் ஹாஸ் டு பி சாட்டிஸ்ஃபை n+1 கண்டிஷன். இப்போ 13th ஆர்டர் எடுத்தோம் அப்படின்னா, ஸோ இட் ஹாஸ் டு கோ ஃபார் அன் 14th வேல்யூ. ஓகே. ஸோ next thing, what you have to see here அப்படின்னா, what are the procedures which you have to use for task-based trajectory planning? So procedure எடுத்துக்கிட்டோம் அப்படின்னா, first thing we have to obtain the function. Okay. So from obtaining the function, we have to go for an sample function. அதுக்கப்புறம் என்ன பண்ணணும்னா, we have to apply IK and Jacobian calculations பண்ணணும். Then we have to fit function functions. So இதுல இருந்து என்ன பண்ணுவோம் அப்படின்னா, we have to take a sample to get the discrete values of it. Okay. So the remaining thing, I hope we can see in the next class. Okay. Thank you.